Welcome to The Explainer, where we take complex scientific sources and transform them into clear, structured insights. Today, we're exploring the fascinating mechanics of soil temperature. You see, heat isn't just some vague feeling. It is literally kinetic energy. It's the random motion and rapid vibration of molecules. And the sheer speed of that vibration inside the Earth fundamentally dictates plant life and survival. Let's get into it.
Here is our roadmap for today. We'll be covering the source of soil heat, thermal properties, how heat actually moves, managing temperatures, the power of mulch, and finally, why temperature matters so much.
Section 1. The source of soil heat.
So our journey starts with the ultimate source of this kinetic energy, incoming solar radiation. But honestly, it's wild how little of that massive solar power actually makes it to the ground. On average, a full 50% of solar radiation never even reaches the Earth. It just gets intercepted by clouds and dust particles. Another 40% is either used up evaporating water from the soil and leaves, or it just reflects right back into the sky. That leaves just a critical 10%. Just 10% is actually absorbed by the soil to drive all those vital plant processes.
Now, that remaining 10% is heavily influenced by a property called albedo. Albedo is basically just the fraction of incoming radiation that bounces off the land surface. If you've got dark-colored rough soil, your albedo is super low, ranging from 0.1 to 0.2, which means those soils are absorbing way more heat. But if the surface is smooth and light-colored, the albedo shoots up to 0.5 or even higher, meaning a massive chunk of that solar energy is just reflected away.
Section 2. Soil thermal properties.
Once that solar heat finally breaks through the surface, how the soil reacts depends entirely on its unique thermal properties. To really understand this, we first have to define specific heat. Think of specific heat as a measure of how stubborn a material is when you try to change its temperature. By definition, it's the quantity of heat required to raise the temperature of a unit body by exactly 1 degree Celsius. And crucially, we always measure this in relation to the heat capacity of water.
This chart brilliantly illustrates why different soil conditions warm up at completely different speeds. Water is our baseline, sitting at a specific heat of 1.00. Air is much higher, at 2.4. But look at dry soil. It's way down at 0.233. And soil-forming minerals? Even lower, at 0.2. What this tells us is that water demands a massive amount of heat to warm up, whereas dry soil or minerals, they heat up incredibly fast with way less energy.
Next up is thermal conductivity. If specific heat is about how hard it is to warm up, thermal conductivity simply measures how well the soil can pass that heat along. It's the quantity of heat passing through a unit area of soil in a given amount of time, driven by the temperature difference between the areas.
Let's see how soil texture plays into this. Actual heat conductance depends on water content, texture, and structure. But generally, conductivity decreases as particle size shrinks. So sand acts like a fast lane. It transfers heat much faster than loam. Loam is faster than clay, and dense peat is the absolute slowest of them all.
Bringing these ideas together, we get thermal diffusivity, which is the ratio of thermal conductivity to heat capacity. This metric tells us the actual speed at which temperature changes happen inside the body of the soil. And here's a really cool detail from the source. If you take the reciprocal of that number, it gives you the soil's thermal retentivity. That tells us exactly how well the soil holds on to that heat once it has it.
Section 3. How heat moves.
Let's dive into the physical mechanics here. How does heat physically get from a hot spot to a cold spot in the dirt? The sources outline 3 primary physical processes for this: conduction, convection, and radiation.
First up is conduction, which is entirely about molecular collisions. It relies completely on the momentum of molecules. As the molecules closest to the heat source warm up, their kinetic energy spikes. They start vibrating much faster, and they literally bump their energy into adjacent molecules. It's like a microscopic game of dominoes, passing the heat from one end to another.
Convection, on the other hand, involves the actual motion of the hot body itself carrying the heat with it. When fluid molecules absorb heat, they expand, their density decreases, and they physically rise up. Cooler molecules then rush in to take their place. But remember, this specific process only happens in fluids.
The final method is radiation. This process completely bypasses the need for physical molecules or any intervening medium. Radiation just transfers energy right through space in the pure form of electromagnetic waves.
Section 4. Managing soil temperature.
Now that we understand the physics, let's look at human intervention. How can we artificially tweak these thermal regimes? For agriculture, it's all about controlling the energy balance. The solar constant, the rate radiant energy hits our atmosphere, is about 2 calories per square centimeter per minute. The energy available to heat the soil is a direct balancing act, catching as much of that incoming radiation as possible while managing what escapes as outgoing long-wave radiation. Trap more than you lose, and the soil heats up. We can actually modify this balance just by shaping the fields. Physical shaping changes the heat flux because the slope and direction dictate how much radiation is captured. Ridges naturally record higher temperatures than furrows. But direction matters too. East-west oriented ridges absorb way more heat and record much higher soil temperatures than your conventional north-south ridges.
Section 5. The power of mulch.
Another massive management tool is mulching. Mulch directly alters albedo, intercepts incoming radiation, and acts as a physical barrier. And the material you choose creates a vast contrast in the microclimate. Look at these specifics. Black plastic reduces outgoing heating, keeping things warm. Paper and straw mulches actually increase outgoing cooling. Aluminum foil sharply increases outgoing cooling. On the flip side, transparent plastic triggers a potent greenhouse effect, while opaque mulches act as a thermal insulator, bringing down the maximum temperatures while raising the minimums.
Section 6. Why soil temperature matters.
Okay, we've covered the complex thermodynamics and management techniques, but let's get to the so what. Why is this microclimate manipulation so critical? Because temperature absolutely dictates plant growth. It triggers seed germination. If temperatures drop too low, crops suffer from impaired water and nutrient absorption. Cold soil actually limits root branching, literally leaving them as these stunted, white, succulent roots. And dangerously, those low temperatures create the perfect storm for parasitic fungal diseases to attack.
It all really comes down to this specific temperature threshold. Soil microbiology and the decomposition of organic matter are incredibly heat dependent. Once the temperature drops below 10 degrees Celsius, microbial activity is severely restricted. And if it hits exactly 5 degrees, it is a hard stop. Decomposition and microbial life absolutely cease. Essential biological transformations like nitrification and aminification just stop entirely.
This brings us to a profound realization to end on. We know heat is the literal kinetic energy driving every single biological reaction in the Earth. And we know how incredibly sensitive this whole system is to just a few degrees of change. So how will you use these principles of albedo and thermal conductivity to tip the delicate energy balance of incoming and outgoing radiation in your crop's favor?